Hi, welcome back to my class in linear algebra. For today, we will take up the Gaussian elimination method for solving system of linear equations. This particular method, Gaussian elimination, will apply for any system of linear equations. A system of linear equations with unique solution, that means there is only one solution. A linear system of linear equations with infinitely many solutions, and to system of linear equations with no solution. That is, a system of linear equations with no solution is known as inconsistent system of linear equation. In the Gaussian elimination method, we use the elementary row operations. That means the Gaussian elimination method makes use of the elementary row operations to find the solution of system of linear equations. And we start with our first example. Consider the following system of linear equations in four variables a, b, c, d. This is a system of linear equations with with three linear equations and four variables. And these are linear equations because the exponent of any of the variables in any of the equations is 1. And the first step in the Gaussian elimination method is to write the augmented matrix. That is a matrix consisting of the coefficients of the variables in the given equations and the constant terms of the equation of the right-hand sides of the equation. We write the coefficients of A in the first column of the augmented matrix. Coefficients of A are 3, 1. In the last equation, the variable A is missing, but you can always add the variable A with coefficient of 0. So you can add 0A here plus B. If you add 0A, the coefficient will be 0. Thus, the coefficients of A are 3, 1, 0. In the second column of the augmented matrix, we write the coefficients of the variable b. We have positive 2, negative 5, and positive 1. In the third column, we write the coefficients of the variable c. We have negative 1. Again, the variable c is missing in the second equation, and you can always add c, but with coefficient of 0. So you can write minus b plus 0c plus 2d. Thus, the coefficients of c are negative 1, 0, 3. And the entries of the fourth column of the augmented matrix are the coefficients of the variable d. We have positive 5, positive 2, and negative 1. And the last column of the augmented matrix consists of the constant terms of the equations, or the numbers at the right-hand sides of the equations. We have 2, 1, 0. And the coefficients are separated from the constant terms of the equation by this vertical line. Now, we will transform this matrix into a lower triangular matrix by using the elementary row operations. In the lower triangular matrix, we should have an increasing number of zeros from the first to the last row. And in the first row, we make the first non-zero entry equal to positive 1. In the first row, the first non-zero entry is 3, and we should make this 1. And we can make this 1 by dividing the first row by the reciprocal of 3, which is 1/3. Or we perform the following elementary row operation. Again, the first non-zero entry in the first row should be 1. And because it is 3, we should make this 1. And we can make this 1. If we make this 1, we should replace all the entries of the first row. And if we want to make this 1, we perform this elementary operation of the first type. That is, we replace the first row by multiplying the entries of the first row by a scalar. In this case, the reciprocal of 3. The number to be changed to 1. Or we simply divide row 1 by 3. We divide each entry of row 1 by 3. And we get 3 divided by 3 is 1. 2 divided by 3 is 2/3. Negative 1 divided by 3 is negative 1/3. 5 divided by 3 is 5/3. And 2 divided by 3 is 2/3. After making the first entry, the first non-zero entry in the first row equal to 1, all the entries below this 1 should be 0. So we must change 1 to 0. And this one will remain, the entries of the last row will remain as is because this entry is already 0. Again, after making the first non-zero entry in the first row equal to 1, all the entries below it must be 0. So we should change this 1 to 0, and this will remain as is because it is already 0, as well as all the entries of the last row. Now, if we want to make this 1 to 0, transform it to 0, or change it to 0, we should replace all the entries of row 2. So we operate on the entries of row 2 by using an elementary operation. The number to be changed to 0 is 1, and you take its negative. Always take the negative of the number to be changed to 0. This positive 1, take its negative, it will become negative 1. If this is negative 1, you take its negative, it will become positive 1. The number to be changed to 0 is 1, we take its negative, negative 1. And we multiply it by row 1. Our row 1 is like our reference row because we are making this 1, 0 with reference to the first non-zero entry in the first row. Plus the second row. This is the second type of elementary row operation, where we multiply a row by a scalar and we add the second row. We perform this operation, multiply row 1 by negative 1. And these are the entries of row 1, 1, 2/3, negative 1/3, 5 over 3, and 2/3. Multiply these entries by negative 1. We multiply the entries of the first row by negative 1, and we get these numbers, negative 1, negative 2/3, 1/3, negative 5/3, and negative 2/3. And to these entries, we add the entries of row 2. Entries of row 2, 1, negative 5, 0, 2, 1. We add negative 1 plus 1 is 0. Negative 2/3 minus 5. for us to have a denominator of 3. For negative 5, we multiply negative 5 by 3 over 3. Negative 5 multiplied by 3 is negative 15. Minus 2 is negative 17. And common denominator is 3. Negative 2/3 minus 5 is negative 17 over 3. 1/3 plus 0 is 1/3. Negative 5/3 plus 2. Again, we multiply 2 by 3 over 3 so that we will have a common denominator of 3. 2 multiplied by 3 is 6. Minus 5 is 1 over common denominator of 3. Negative 5/3 plus 2 is 1/3. And negative 2/3 plus 1, multiply 1 by 3 over 3 so that common denominator is 3. 3 minus 2 is 1 over common denominator of 3. Hence, negative 2/3 plus 1 is 1/3. The entries of the first row are as is: 1, 2/3, negative 1/3, 5/3, and 2/3. And the entries now, the new entries of row 2 are 0, negative 17 over 3, 1/3, 1/3, 1/3. And since this element is already 0, we just copy the entries of row 3. 0, 1, 3, negative 1, 0. The leading entry, non-zero entry in the first row is 1, and all the entries below 1 are 0. Next, we go to the second row. The first non-zero entry in the second row is negative 17 over 3. And we make this equal to, we change this negative 17 over 3 to positive 1. To change negative 17 over 3 to positive 1, we have to replace all the entries of row 2 using an elementary operation for row 2. And to change negative 17 over 3 to 1 is simply multiply row 2 by the reciprocal of this number to be changed to 1. Negative 17 over 3, its reciprocal is negative 3 over 17. The elements of row 3 will be replaced by multiplying the elements of row 2. The elements of row 2 will be replaced by multiplying the elements of row 2 by negative 3 over 17, which is the reciprocal of negative 17 over 3. The element to be changed to 1. The elements of the first row are as is. We now perform this elementary operation. We multiply row 2 by negative 3 over 17. 0 multiplied by negative 3 over 17 is 0. Negative 17 over 3 multiplied by its reciprocal negative 3 over 17 is 1. 1/3 multiplied by negative 3 over 17. 3 in the numerator will cancel out with 3 in the denominator, and you get negative 1 over 17. 1/3 multiplied by negative 3 over 17 is negative 1 over 17. And 1/3 multiplied by negative 3 over 17 is negative 1 over 17. The entries of the last row as is 0, 1, 3, negative 1, 0. Zero, 1, 3, negative 1, 1. Now the first non-zero entry in the first row is 1 and all the elements below it are 0. The first non-zero element in the second row is 1 and we should make all the entries below it 0. And there is only one element below it, which is 1. And this one we have to change to 0 by again performing an elementary operation of the second type. If we have to change this to 0, we must replace all the entries of row 3. And we changed 1 to 0 with reference to row 2 because 1 is directly below the first non-zero entry in the second row. So our second row, R2, is our reference row. Again, if we change 1 to 0, we have to replace all the entries of row 3. The number to be changed to 0 is 1 and we take its negative 1. And as I said, our reference row is row 2 because this number to be changed to 0 is directly below the first non-zero entry in the second row, 1. And to this, we simply add R3. We perform this operation, multiply the entries of row 2 by negative 1. 0 multiplied by negative 1 is 0. 1 multiplied by negative 1 is negative 1. Negative 1 over 17, negative 1 over 17, negative 1 over 17. Each of these we multiply by negative 1. And we get positive 1 over 17, positive 1 over 17, and positive 1 over 17. And to this row of entries, we add the entries of row 3. 0, 1, 3, negative 1, 1. We now perform the operation addition. 0 plus 0 is 0, negative 1 plus 1 is 0. And we have 1 over 17 plus 3. Again, to get a common denominator of 17, multiply 3 by 17 over 17. And 17 multiplied by 3 is 51 over 17. 51 plus 1 is 52 over 17. 1 over 17 minus 1, again, to have a common denominator of 17, we multiply negative 1 by 17 over 17, and we get negative 17 plus 1 is negative 16 over common denominator of 17. One over 17 plus 1, we multiply 1 by 17 over 17. 17 plus 1 is 18 over common denominator of 17. And these are the new entries of row 3. The entries of the first and second rows are the same. This matrix is said to be equivalent to this matrix because this matrix is obtained from this matrix by elementary operation. Similarly, this matrix is equivalent to this matrix, and this matrix is actually equivalent to the original augmented matrix because this matrix is obtained by a sequence of elementary operations from the original augmented matrix. Now, we expect if you have an increasing number of zeros from the first to the last row, then you stop because that means your matrix forms a lower triangular matrix with increasing number of zeros from the first row to the last row. In the first row, the first non-zero entry is 1 and there is no zero preceding 1, or there is no zero that comes before 1. So the number of zero in the first row before the first non-zero entry is 0. In the second row, the first non-zero entry is 1 and there is 1 0. Before 1, the first non-zero entry in the second row. So in the first row, we have 0. The number of 0 preceding the first non-zero entry in row 1 is 0. In the second row, the number of zeros preceding the first non-zero entry in the second row is 1. So the number of zeros from the first to the second row increases from 0 to 1. In the second row, the first non-zero entry is 52 over 17. And the number of zeros preceding 52 over 17, or the number of zeros that come before 52 over 17, is 2. So in the first row, we have 0. The number of zeros preceding or that comes before the first non-zero entry in the first row, 1 is 0. In the second row, the number of zeros that comes before the first non-zero entry in the second row, 1 is 1. In the third row, the number of zeros that comes before the first non-zero entry in the third row, 52 over 17, is 2. So the number of zeros increases from 0 to 1 to 2. Therefore, this matrix now form a lower triangular matrix that is the zeros. Below the zeros, the number of zeros that increases from the first to the last row form a triangle. That's why it's called a lower triangular matrix, and these zeros, if it's a square matrix, are below the diagonal. That's why it's called lower triangular matrix. And if you obtain a lower triangular matrix, that means you stop. And the next step is to write the linear equations again from the augmented matrix. Before we write the linear equations again from the augmented matrix, I would like to make a correction. The entries in the last row are 0, 1, 3, negative 1, 0, 0, 1, 3, negative 1, 0, 0, 1, 3, negative 1, and this should be 0. 0, 1, 3, negative 1, 0, this should be 0. And when we perform this operation, we add the entries of row 3, 0, 1, 3, negative 1, 0, 0, 1, 3, negative 1, 0. And if we add 1 over 17 plus 0 is 1 over 17. Hence, the new entries of the last row should be 0, 0, 52 over 17, negative 16 over 17, and 1 over 17, not 18 over 17. This should be 1 over 17. We now write the linear equations again from this augmented matrix. You recall that when we write the original augmented matrix, we take the entries of the first column as the coefficients of the variable a in the given system of linear equations, and the entries of the second column are the coefficients of the variable b in the given system of linear equations, and the same with the third and fourth columns. And the last column of the augmented matrix are the constant terms of the given system of linear equations. So if we write the first linear equation from this augmented matrix, 1 will be the coefficient of A. These numbers are the coefficients of B. These entries in this column are the coefficients of C. And these entries in this fourth column are the coefficients of variable D. And these entries in the last column of the augmented matrix are the constant terms or the right-hand sides of the linear equations. Hence, the first linear equation is 1a plus 2/3 b minus 1/3 c plus 5/3 d is equal to 2/3. And the second linear equation, if you multiply 0 by a, that would be 0. So you start with 1b, 1 multiplied by b is b, minus 1 over 17c, minus 1 over 17d is equal to negative 1 over 17. And the last linear equation is the coefficient of a, 0. This is the coefficient of b, 0. But you multiply a variable by 0, you get 0. So the last equation is actually 52 over 17 multiplied by c minus 16 over 17 multiplied by d is equal to 1 over 17. Again, we write the linear equations from this augmented matrix A plus 2/3 B. But we can simplify each of these linear equations by removing the denominator. For the first linear equation, if we want to remove the denominator 3, we multiply both sides of the first linear equation by 3. So a multiplied by 3 is 3a. 2/3 b multiplied by 3 is 2b. Minus 1/3 c multiplied by 3 is negative c. 5/3 d multiplied by 3 is 5d. Is equal to 2/3 multiplied by 3 is 2. In the second linear equation, we remove the denominator 17 by multiplying the whole equation or multiplying both sides of this second linear equation by 17. 17 multiplied by b is 17b. Minus 17c minus 1 over 17c multiplied by 17 is minus c. Minus 1 over 17d multiplied by 17 is minus d. Is equal to minus 1 over 17 multiplied by 17 is negative 1. Finally, we remove the denominator 17 from the last equation by multiplying the left-hand side and the right-hand side of this equation by 17. And the denominator 17 will be eliminated, and you get 52 over 17. C multiplied by 17 is 52c. Minus 16 over 17d multiplied by 17 is minus 16d. Is equal to 1 over 17 multiplied by 17 is 1. Now, this is an example of a system of linear equations with infinite solutions. And if you have a system of linear equations with infinite solutions, there will be free variables. A free variable is a variable that can be assigned any number, any real number. And usually we take if you have the variables A, B, C, D, we take the last variable as free variable, or we make the last variable as free variable. But any of these variables A, B, C, D can be a free variable, and that variable can be assigned any value or real number. Again, if you have a system of linear equations where you have more number of variables than number of equations, or the number of variables is greater than the number of equations, then your system of linear equations has an infinite solution, and some of the variables will be free. One or more of the variables will be free, and the number of free variables is equal to the number of variables minus the number of equations. Again, the number of free variables is equal to the number of variables minus the number of equations. From this system, or from this equivalent system of linear equations, this is an equivalent system of linear equations equivalent to the original given of system of linear equations. Because this system of linear equations is obtained from this augmented matrix, which is equivalent to the original augmented matrix. And the number of variables is 4, A, B, C, D, that's 4. Minus the number of equations, we have 1, 2, 3, or from the augmented matrix, the number of equations we derive from the augmented matrix is 1, 2, 3, 3. Hence, the number of free variables is 1. That means you have to choose among A, B, C, D, one variable to be your free variable. And as I said, we usually take the last variable as the free variable, and we solve the values of the other variables in terms of that free variable. So from the last equation, we solve for C in terms of the variable D, by transposing negative 16 over negative 16d to the right-hand side. We transpose negative 16d to the right, we get positive 16d. At the left-hand side, we are left with 52c. And we are solving for C in terms of our free variable D. So we divide both sides by 52. And this is the value of C, 1 plus 16D all over 52. Where the variable D is free, that means you can assign any value to D. If you assign a value to D, once you assign a value to D, you can compute for the value of C. Now, from the second equation, we now solve for B in terms of D also, in terms of the free variable D. We transpose negative C and negative D to the right-hand side. At the left-hand side, we are left with 17b. 17b is equal to negative 1 plus c plus d. And to solve for b, we now divide both sides of this equation by 17. And we get b equals negative 1 plus c plus d all over 17. And as I said, we write the values of the other variables in terms of the free variable. And see, here is not a free variable. The free variable, our free variable is d. So we replace c with its value in terms of the free variable d, 1 plus 16d over 52. And we simplify this expression. We take the common denominator 52. For us to get a common denominator of 52, we multiply negative 1 by 52 over 52. Multiply d by 52 over 52. And you get 52d plus 16d. That's 78d. And we multiply negative 1 by 52 over 52. That's negative 52 plus 1. That's minus 51. Again, we take the common denominator 52, we multiply negative 1 by 52 over 52, you get negative 52 plus 1 is negative 51. And we multiply d by 52 over 52, that's 52d plus 16d equals 78d. Common denominator is 52 and we multiply 52 by 17. And this is the value of b in terms of the free variable 78d. In terms of the free variable d, the value of b is 78d minus 51 all over 52 times 17. Now we have the value of b, c, and the variable d is free. From the first equation, we now solve for a in terms of d. We now solve for the value of a in terms of the free variable d. So far, we obtained the values of c in terms of d. C is equal to 1 plus 16d over 52. We also obtained the value of b in terms of the free variable d. b is 78d is equal to 78d minus 51 all over 52 times 17. Now we find the value of a from the first linear equation we obtained from the last equivalent augmented matrix. From this equation, we solve for a in terms of b, c, and d. We transpose 5d to the left. It becomes minus 5d. We transpose negative c to the right. We transpose 5d to the right. It becomes minus 5d. We transpose minus c to the right. It becomes plus c. And we also transpose 2b to the right, it becomes minus 2b. So 3a is equal to but we want to solve for a, so we divide this equation, both sides of this equation by 3. But we want to express the value of a in terms of the free variable d. but B and C are not free variables, but their values are expressed in terms of the variable D. So we replace C and B with these values in this equation, and we simplify. We have 2 minus 2B. B is 78D minus 51 over 52 times 17. We multiply that by minus 2. Plus the value of C, 1 plus 16D over 52. Minus 5D. All over 3. Again, we take a common denominator. We can reduce 2 over 52 to lowest terms, but we will not do that. We will take 52 times 17 as the common denominator. In the first term, we multiply 2 by 52 and 17. We multiply 2 by 52 times 17 over 52 over 17. So that the common denominator is 52 times 17. In the second term, we have minus 2 times 78D. That's 78 multiplied by 2 is 156D. 2 times 78D is minus 156D. Negative 2 multiplied by negative 51 is 100. Positive 102. And this term we multiply by 17 over 17 so that we have 52 times 17 in the denominator. We multiply 1 plus 16D by 17. And the last term, minus 5D, we multiply by 52 multiplied by 17. The common denominator is 52 multiplied by 17. And the common denominator we multiply by 3. And we make use of our calculator to compute the product 2 times 52 times 17 and 3 times 52 times 17. And we will combine like terms. The last terms is minus 5D multiplied by 52 multiplied by 17. This should be minus 5D. And we get our calculator. Before we continue, I would like to make another correction for the value of B. The value of B is 68D minus 51 over 52 multiplied by 17. Earlier, I wrote B as 78B. It should be 68 obtained from the sum of 52 and 16. 52 plus 16 is 68, not 78. So B now is 68, D minus 51 over 52 multiplied by 17. And from here, from the last equation we obtained from the last augmented matrix, the value of A is 2 minus 2B plus C minus 5D all over 3. We replace B with 68, D minus 51. 78 should be 68D minus 51. And C is 1 plus 16D all over 52. We multiply 2 by 68. We should get 136 instead of 156. 2 multiplied by 68 is 136. And we continue from here. We multiply 2 by 52 by 17, and using calculator, you should get 1,768 minus 136D plus 102. 17 multiplied by 1 is 17. 17 by 16D is 700. 272D minus 5 multiplied by 52 multiplied by 17 is negative 4,420D. Minus 5 multiplied by 52 multiplied by 17 is negative 4,420D. In the denominator, we have the same 3 multiplied by 52 by 17, and we combine like terms in the numerator, beginning with the terms with D minus 136D, negative 136D plus 272D minus 4,420D. Using calculator, you should get negative 4,284D. And we add the terms without D, 1,768 plus 102 plus 17. You should get 1,887. And this is the value of A in terms of the free variable D. Now we write the general solution, the values of A, B, C in terms of the free variable D. It's called general solution because the variables have no specific numbers or values. The values of the variables are expressed in terms of the free variable D. So the general solution, the value of A is negative 4,284D plus 1,887 all over 3 times 52 times 17. And the value of B is 68D minus 51 all over 52 multiplied by 17. And the value of C is 1 plus 16D all over 52, where the variable D is free, which means that you can assign any number to D, and once you assign a value to D, you can find the values of C, B, and A. And if you have particular values for the variables, we call that solution particular solution. We now obtain one particular solution corresponding to one value of the free variable D. For a system of linear equations with infinite solutions, you always start by assigning values to the free variable. Assign any number or value to the free variable D. And to simplify, to get one of the particular solutions, we assign D a value of 0. Because D is free, D can have any value, and I will assign a value of 0 to D. If you change the value of D, the value of A, B, and C will also change, and you get a different particular solution. So this system of linear equations is said to have infinite solutions because it has infinitely many particular solutions. corresponding to the values of the free variable d. For this particular value of the free variable d0, we generate one particular solution. So if d is equal to 0, the value of c, or you may start from a. If d is 0, the value of a is 1,887 all over 3 multiplied by 52 multiplied by 17. For the value of d equals 0, the value of b is 68 times 0 minus 51. That's minus 51 over 52 times 17. And the value of c, if d is equal to 0, c is equal to 1 multiplied by 16 times 0, that's 0, 1 over 52. And this is one particular solution corresponding for the value 0 for the free variable d. If you assign another value for d, say 1 or negative 1, the values of a, b, c will change and you get another particular solution. Now to check if this particular solution is correct, we substitute the values of a, b, c, and d to the original system of linear equations. We now check if our particular solution, the set of values for a, b, c, d are correct. And we should substitute these values of a, b, c, d, and these equations must be satisfied if they are correct. And you may start from the last equation or you may start from the first equation. I will start from the last equation. The value of b is negative 51 over 52 times 17. Plus 3 multiplied by the value of c. The value of c is 1 over 52. Minus d, but the value of d, we assign a value of 0 for d. And when we simplify this, the answer should be 0. 51 over 17, negative 51 over 17 is negative 3 over 52 plus 3 over 52 is equal to 0. Thus, the last equation is satisfied because when the values of b, c, and d are substituted into the last equation, the sum is equal to 0. Now we check if the values of a, b, c, d are correct. We substitute the values of the variables into equation 2. A is equal to 1,887 over 3 times 52 times 17. Minus 5 multiplied by b, and b is negative 51 multiplied by negative 5, that's positive. 5 multiplied by b, 51 over 52. Plus 2 multiplied by d, but d is equal to 0 multiplied by 2 is 0. Now we check if this will give us a sum of 1. For us to get an LCD, common denominator of 3 times 52 times 17, we multiply the second term by 3 over 3. So that common denominator is 3 times 52 times 17. So we multiply 15 by 51 and we add 1887, 1887. We multiply 15 by 51 in the second term. And we get 765 plus 1887 in the first term. And we get 2652. In the denominator, common denominator is 3 multiplied by 52 multiplied by 17. And that should equal to 2652. So that 2652 in the numerator divided by 2652 in the denominator will be equal to 1. We check if 3 multiplied by 52 multiplied by 17 is equal to 2652. Thus, the second equation is also satisfied because when we substituted the values of A, B, D, and we simplify, the result is equal to 1, which is the right-hand side of equation 2. Now, we check the first equation by substituting the values of A, B, C, D, where D, the free variable, is equal to 0. We start with 3 multiplied by A. And if you multiply A by 3, the 3 in the numerator over 3 in the denominator will cancel out. And 3A simplifies to 1887 divided by 52 times 17. The second term is 2B. 2 multiplied by B. B is 51 over 17. Minus 51 over 17 is negative 3. Negative 3 over 52. So negative 3 multiplied by 2 is negative 6. Negative 6 over 52. I already divided minus 51 by 17, that's negative 3 multiplied by 2 is negative 6. Minus C minus 51 minus 1 over 52. We want a common denominator of 52 multiplied by 17. So we multiply these last two terms by 17 over 17, or minus 6 minus 1 is negative 7 multiplied by 17. And that's negative. We subtract that from 1887. We have negative 7 multiplied by 17. And we subtract that from 1887. And we should get 1768. And we divide that by 52 multiplied by 17. 52 multiplied by 17 is 884. And we divide 1768. We divide by 884. And we get 2. Which is the right-hand side of the first equation 2. And this means that the first equation is satisfied for the values of A, B, C, D. And all the equations, all the given equations in the given system are satisfied for the values in this particular solution. Therefore, the set of values for this particular solution are correct. We now take an example of a system of linear equations where the number of equations is equal to the number of variables and the solution is unique. And we will solve this system of linear equations by Gaussian elimination. For our second example, consider the following system of linear equations. We have x plus 2y minus 3z is equal to 0, minus 2x plus 3y plus z is equal to 2, 3x minus y plus 2z is equal to 4. Again, we will try to solve this system of linear equations by Gaussian elimination, and we expect if this system has linear equation, the solution is unique. Because we have unique solution for a given system of linear equations if the number of equations is equal to the number of variables. If the number of variables is greater than the number of equations, then you expect to have an infinitely many solutions for the given system of linear equations, and you should have some pre-variables, and the number of pre-variables is equal to the number of variables minus the number of equations. But if you have a system of linear equations such as this one, where the number of equations is equal to the number of variables, then you expect the system of equations to have a unique solution, that is only one solution. And to solve this by Gaussian elimination, we write the augmented matrix by taking the coefficients of the variables and the constant terms of the equations. This is the augmented matrix consisting of the coefficients of the variables. The entries of the first column of the augmented matrix are the coefficients of the variable x. We have positive 1, negative 2, and positive 3. The entries of the second column are the coefficients of the variable y in the given system. We have 2, 3, and negative 1. And the entries of this third column are the coefficients of the variable z in the given system, minus 3, positive 1, and 2. And the entries of the last column of the augmented matrix are the constant terms of the equations 0, 2, 4. And we transform this into lower triangular matrix. Since the matrix of the coefficients of the variables is a square matrix, in the lower triangular matrix, the entries below the main diagonal, the diagonal entries are 1, 3, 2. The entries below the diagonal, those are the entries negative 2, 3, negative 1, must be 0. So that they will form a triangle below the diagonal. That's why it's called lower triangular matrix. And again, we start with the first row. The first non-zero entry in the first row must be 1. And since it's already 1, we take the entries of the first row as is. We will not change any of the entries of the first row. Instead, we make all the entries below 1, negative 2 and 3, to 0. The first non-zero entry in the first row is already 1. And we should make all the entries below 1, 0. So if we have to change negative 2 to 0, we have to change all the entries of row 2. And the number to be changed to 0, we take its negative. We take the negative of the number to be changed to 0. The number to be changed to 0 is negative 2, and its negative is positive 2. And we multiply positive 2 by row 1 because row 1 is our reference row. That means this number negative 2 is below the first non-zero entry in the first row, row 1, which is 1. The first non-zero entry in the first row is 1. Therefore, row 1 becomes our reference row. And to 2R1, we add R2. We perform this operation to get the new entries of row 2. Multiply row 1, the entries of row 1 by positive 2. 1 multiplied by 2, 2 multiplied by 2, negative 3 multiplied by 2, and 0 multiplied by 2. And the answer should be 2, 4, negative 6, 0. And to 2R1, we add the entries of row 2. The entries of row 2 are negative 2, 3, 1, 2. We perform the operation addition. 2 plus negative 2 is 0, 4 plus 3 is 7, negative 6 plus 1 is negative 5, and 0 plus 2 is 2. And these are the new entries of row 2. You can see that the first entry in row 2 is now 0. This 0 will be under 1. We also change 3 to 0. If we want to change 3 to 0, we have to change all the entries of row 3 by performing an elementary row operation. And we take the negative of the number to be changed to 0. The number to be changed to 0 is 3. We take its negative, we get negative 3. And again, we multiply negative 3 by our reference row, row 1, because row 1 is the row with the first non-zero entry 1 in each row. And 3 is under. And this first non-zero entry in row 1 has 3 below it, the number to be changed to 0. And to negative 3, R1, we add R3. We perform this elementary row operation by multiplying all the entries of row 1 by negative 3. 1, 2, negative 3, 0, multiply by negative 3. And we get negative 3, negative 6, positive 9, 0. And to these entries, we add the entries of row 3. 3, negative 1, 2, 4. We perform the operation addition. Negative 3 plus 3 is 0. Negative 6 plus minus 1 is negative 7. 9 plus 2 is 11. And 0 plus 4 is 4. We now write the matrix equivalent to this augmented matrix. The entries of the first row are as is. The new entries of the second row are 0, 7, negative 5, 2. And the new entries of the last row are 0, negative 7, 11, negative 4. So, 0, negative 7, 11, positive 4. Now we inspect the second row. In the second row, the first non-zero entry in the second row is 7. And we should make this 1. To make this 1, we divide all the entries of row 2. If we want to change 7 to 1, we have to change all the entries of row 2 by multiplying row 2 by the reciprocal of 7, the number to be changed to 1. And this is the elementary row to change 7 to 1. That is, you divide all the entries of row 2 by 7. Or multiply all the entries of row 2 by the reciprocal of 7, which is 1 over 7. The entries of row 1 are the same. Entries of row 3 are the same. The new entries of row 2, 0 divided by 7 is 0. 7 divided by 7 is 1. Negative 5 divided by 7. And 2 over 7. The entries of the last row are the same. 0, negative 7, 11, positive 4. We are now in the second row. The first non-zero entry is now 1. All the entries below this 1 in the second row, the first non-zero entry in the second row must be changed to 0. And there is only one entry below positive 1 in the second row, the first non-zero entry in the second row, which is negative 7, and negative 7 must be changed to 0. If we change negative 7 to 0, we have to change all the entries of row 3. The number to be changed to 0, we take its negative. The number to be changed to 0 is negative 7, and its negative is positive 7. And we multiply positive 7 by row 2. Our reference row is now row 2 because negative 7 is under 1, the first non-zero entry in row 2. And to 7 multiplied by R2, we add R3. Again, this is the second type of elementary row operation. Multiply row 2 by positive 7. We have 0 multiplied by 7, 1 multiplied by 7, negative 5 multiplied by 7, and 2 multiplied by 7. And we get 0, 7, negative 5, 2. And to these entries, we add the entries of row 3. 0, negative 7, 11, 4. And the new entries of row 3 are 0, 0 plus 0 is 0, 7 plus negative 7 is 0, negative 5 plus 11 is 6, and 2 plus 4 is 6. The entries of the first and the second rows are the same. The entries of the first two rows are the same, and the new entries of row 3 are 0, 0, 6, and 6. Now, this augmented matrix forms now a lower triangular matrix because the number of zeros from the first to the third row is increasing. In the first row, the number of 0 preceding or that comes before the first non-zero entry in the first row is 0. The number of 0 in the second row that precedes the first non-zero entry 1 in the second row is 1. So the number of zeros from the first to the second rows increases from 0 to 1. In the last row or third row, the number of zeros preceding or that comes before the first non-zero entry, 6 in the third row is 2. So the number of zeros increases from 0 to 1 and then 1 to 2. And these zeros form a triangle below the diagonal. Now we write the linear equations from this equivalent augmented matrix, from this matrix equivalent to the original augmented matrix. And the first column entries are the coefficients of the first variable x. The entries in the second column are the coefficients of the second variable y, and the third entries are the coefficients of the last variable z. And the last column are the right-hand sides of the equations. So the first equation is x plus 2y minus 3z equals 0. The second equation is 1 multiplied by y, we have 0x is 0, plus 1y or y minus 5 over 7z equals 2 over 7. And the last equation is 0x plus 0y plus 6z, 0x and 0y are 0. So the last equation is simply 6z equals 6. And from the last equation, the last equation is 6z equals 6. And from the last equation, you can see if you divide both sides by 6, you get the value of c, which is equal to 1. And substitute the value of c into this second equation. If c is equal to 1, you get y equals 2 over 7 plus 5 over 7. That's 2 over 7 plus 5 over 7 is 7 over 7, or y is equal to 1. And we substitute the values of y, 1, and z, 1 in the first equation. X now is equal to 2, x plus 2 minus 3, because c is 1. And 2 minus 3 is negative 1. We get x minus 1 equals 0. And transpose negative 1 to the right-hand side, you get x equals 1. And we get the solution of the given system of linear equations. All the variables have the same value, equal to 1. And to check, we substitute those values of x, y, z in the original system of linear equation. X is 1, y is 1, z is 1. The first equation is 1 plus 2 minus 3 is equal to 0. In the second equation, x is 1, y is 1, z is 1. You get minus 2 plus 3 is 1 plus 1 is 2. In the last equation, x is 1, y is 1, z is 1. We get 3 minus 1 is 2 plus 2 is equal to 4. Therefore, the given system of linear equations are satisfied by these values of x, y, z all equal to 1. And the solution of the given system of linear equation is said to be unique, which means that the given system of linear equations has no other solutions except this one solution. And that solution is called unique solution. If you continue from here, from this augmented matrix, and you transform this into an identity matrix by changing this 2 to 0 and negative 3 to 0, and minus 5 over 7 to 0, and 6 to 1, so that this part of the augmented matrix becomes an identity matrix. Then you will get directly the value of z is 1, y is 1, and x is 1. And you should try that. You start by making this 1, and to change 6 to 1, you divide row 3 by 6, and you will get 0, 0, 1, 1. And the entries above this one, these two entries should be changed to 0 using the second type of elementary operation, and these two should also be changed to 0. But you do not have to do that. You only have to transpose the augmented matrix into lower triangular matrix, and from there you can solve the values of the variables in the given system of linear equations. For your practice, please try the following exercises. Solve the following given system of linear equations by Gaussian elimination. Number 1, we have m minus n plus u plus b is equal to 1. Second linear equation, 2n minus u plus 3b is equal to 0. And the third linear equation, minus m plus 2u minus b equals negative 1. You notice that in this system of linear equations, the number of variables is greater than the number of equations. So you expect to have a pre-variable for this system of linear equations, and you must give the solution in general terms, that is, give the general solution and give one particular solution for this system of linear equation by assigning any value to the free variable. And please check your solution by substituting the values of the variables into the original system of linear equations. In number 2, we have 2a minus b plus c plus d equals 3. Second equation, minus a plus 2b minus d equals negative 3. Third equation, 3b minus 2c equals 2. Minus 3a plus b plus 2d equals 1. In the given system, as well as in the second system of linear equations, some variables are missing in some of the equations, but you can always add these missing variables by making their coefficient 0. And you notice in the given system of linear equations in number 2, the number of variables is equal to the number of equations. Hence, when you solve this system of linear equations by Gaussian elimination, you expect to get a unique or only one solution. And that completes our lesson for today on Gaussian elimination. If you have question about the lesson today, please ask your question in the comments below. Thank you for joining me in my class today in linear algebra.